For this last part of the tutorial, we'll be interested in actual decoding real signals, and to decode real signals we need to address all the layers from the hardware to the logic bit organization. So let us start with the actual binary phase shift keying Bpsk modulation. So the natural output of a software-defined radio is complex numbers because the spectrum is not an even function, and the mixing of the radio frequency signal with a local oscillator creates two components, I and Q, identity and quadrature, and these I and Q components will allow us to recover the magnitude as square root of I squared plus Q squared, and the phase as arctangent of Q over I. So GPS is using this binary phase shift keying modulation scheme, where we see here the beginning of a sine wave, and then we have this phase flipping, which means that there is a bit change to a new value, then there is a new phase flipping over here, meaning that all these guys are the same bit state until we get the new phase flipping, and so on. So binary phase shift keying requires that we recover the carrier to be able to identify what a phase is. Indeed, a phase only makes sense with respect to a carrier frequency. So if we consider that we have at a given time transmitted a sine wave with some phase flipping that encodes the information, so the data have been at some point generated, so that here, for example, we have this phase flipping, and then again over here. In order to recover the phase value, we actually need to synthesize the original carrier that was transmitted. And a phase locked loop, a PLL, will not be sufficient because there is a random offset in the set point of a phase locked loop output. So we need a trick to actually regenerate locally the carrier that was transmitted by the satellite so that we can extract the phase information. What is the trick for generating the carrier? The fact is that the phase in an Npsk, so an N phase value Psk phase shift keying sequence, the phase is equal to 2 pi divided by N, the Npsk, multiplied by an integer which is included between 0 and N minus 1. So this is an integer value. So the phase is equal to 2 pi over n. In our case, for n equals 2 for Bpsk. Then we see that we have two phase states. N equals 2 means we have phi equal 0 or pi. So we have two positions, phi equals 0 or pi are the two phase value that can be accessible in Bpsk. So the trick to create this carrier is to actually square the signal, or in general taking the nth power of the signal. If you consider that exponential of j delta omega t plus phi, delta omega is the frequency offset between your local oscillator and the remote oscillator, and there is always a leftover. Remember, we have atomic clocks, and even if we have an atomic clock on ground, we might always have the Doppler shift. So this delta omega is the frequency leftover between the transmitted signal and the local oscillator of the receiver, and phi is the random information that was transmitted. So when you have this delta omega and this phi, this means that I can express this term here as being one big phase from here. This I can write as phase phi, and this phase phi has two components which can express as the linear drifting phase and the random sequence which I want to detect. And if I have this, it means I have the phase drifting over time. The drift is rising at rate delta omega and prevents me from detecting the small phi, the phase variation I wish to detect. So the objective is to cancel this term delta omega in order to recover only the random message that was transmitted. So how do we actually cancel this delta omega? The trick is to take, for an Npsk modulated signal, the signal to the nth power. You see that if I take the signal to the nth power, then I introduce the exponent into the argument, so I have n times delta omega plus n phi, and if I multiply this phase value, this possible phase value, by n, you see that these make n and n cancel, and I end up with 2 pi times an integer. But 2 pi times an integer is 0 modulo 2 pi. So this phase quantity here will be cancelled because it's always a multiple of 2 pi, and I'm only left with n times delta omega, so n times the frequency offset. So if I get n times the frequency offset, it means I can cancel, because dividing a frequency is just a matter of introducing a counter. How would you actually create this binary phase shift keying? A very simple way of creating a Bpsk signal is to feed a mixer, on the one hand on the local oscillator with a carrier frequency. In this example, the carrier frequency is the blue curve over here, is a 1.2 gigahertz signal source, and the intermediate frequency part of the mixer is fed with the Bpsk modulation signal here, 100 kilohertz square wave. Just be careful that the intermediate frequency here must not leak any DC current, or otherwise you might damage the diodes of the mixer. So make sure you introduce a DC blocking capacitor, and what you see at the output is the binary phase shift keying, so the phase flipping between 0 or pi on this example. And you see here that if I square the signal, and in this example I can either use the squaring capability of the oscilloscope, of the digital oscilloscope, or I can take a second mixer and multiply the signal by itself. What you see here is that if I take the Bpsk modulated signal and I square it, this is a simulation using MATLAB, I cancel the modulation and I'm left with a pure carrier. If I look at the spectra was initially the 2 sidebands, and the carrier had been cancelled, and when I square the signal I'm left with a clean carrier. You might actually think these are 2 side lobes, but this is because the signal is ideal and there is no noise. If there were some noise on this signal, these 2 side lobes would be hidden under noise. So this is a clean carrier. This was the original signal. We have been able to recover the carrier, and if we are able to recover the carrier, then we can actually detect the random phase variations. This approach is actually applicable to any Npsk, with n the number of phase positions. And as an example to illustrate this aspect, we consider Qpsk, the quad phase shift keying. In a Qpsk signal, we have 4 phase values. So in a Qpsk signal, we have phi, so n equals 4. In this case, we have the values of phi equals 0, pi over 2, pi or 3 pi over 2, and this means that for each clock sequence we create 2 bits. We will transmit 2 bits because we have 4 possible states, and 2 to the 2 is 4. So if we get such a signal, for example here from the Meteor M2 Russian weather satellite, here you see that the raw signal has some spectrum spreading from the digital communication. So this is the modulation that was holding the information that is transmitted to the Earth. You see that if we square the signal, then you have not a 2psk, because Bpsk would still have some spectrum spreading. So this is not a Bpsk signal. And you see that with the 4th power, we actually get a clean carrier here. And this clean carrier is indeed at 4th at 4 times the frequency offset. If we get 4 times the frequency offset, we can cancel this frequency offset. And if you remember that this offset is equal to the fact that this big phi is equal to delta omega, the frequency offset between the transmitter and receiver, times t, the time dependent, plus the random phase that we wish to detect. And now, if we have identified here the delta omega, then we can run this through a counter in order to cancel this term. And if we cancel this term, instead of having a linearly rotating phase at rate delta omega that is superimposed with the phase variation, this is delta omega t, as if I plot the phase as a function of time, then if we cancel delta omega, we are left with only the random evolution of a phase, and we will be able to process this data. In terms of constellation, you will see your constellation here with 4 possible phase states stop rotating as long as delta omega is left. There is a time rotation of a constellation which stops rotating when delta omega is cancelled. So how do you actually feed the whole sequence? We have an antenna with its preamp and the mixing with the local oscillator, and the mixing with the local oscillator leaves us with a frequency offset delta omega that we wish to cancel. And how we do this is we take the nth power of the signal that is Npsk, and by taking the nth power, we are left with a clean signal at n times delta omega, the frequency offset. So we need to divide this, and to divide the frequency by n, we have a counter that allows us to divide the frequency by n. And the output of a counter, which is at delta omega, the clean carrier, will be mixed with the original signal over here, and this mixing will cancel the frequency offset and leave us with a term of phi only. This operation is so common that is implemented in GNU radio. It is called a Qpsk loop. Qpsk loop is the block, the signal processing block, for recovering the phase and cancelling the carrier offset between the received signal and the local oscillator by taking the nth power and dividing the output frequency by n, so that we are left with delta omega. Mixing the return signal with delta omega cancels this frequency offset and leaves us only with a random term delta omega. The only limitation that needs to be taken care of when using the Qpsk loop is that all signal must remain within baseband. The signal must not leave the baseband ranging from -half a sampling frequency to half a sampling frequency. In these charts, you see here an example where we have shifted the signal. This is a Bpsk signal that was shifted a little bit to the left on purpose, so that taking the square of the signal actually shifts by twice the frequency offset. We initially had a frequency offset delta f, now we have twice the delta f. And by squaring the signal, we see that all the side lobes have shrunk and the carrier is by far dominant in all these frequency components. And so the output of a Qpsk loop here on the top left is centered on 0. So the Qpsk loop has compensated for this frequency offset, and the phase output after demodulation and frequency offset compensation by Qpsk loop is a square wave as was transmitted. If this time we shift the frequency too far, you see here that we have taken this phase modulated signal and shifted it further to the left. Well, this time the Qpsk loop is unable to compensate for this frequency offset, and you are left here with the random phase fluctuation overlaid with the frequency rotations due to delta omega times t. Why is it that the Qpsk loop was unable to cancel the frequency offset? Because if now we took twice the frequency offset when we square, we see that twice the frequency offset leaves the baseband. We go beyond the Nyquist frequency, and actually we get back through the positive frequency here, meaning that the control would actually go in the wrong direction. We would, Qpsk loop would detect a positive frequency offset when it is actually negative, and this is because twice the frequency left the baseband. So the limitation in an Npsk signal is that we take the nth power of the signal, meaning that the carrier frequency is shifted to n times delta omega, and this n times delta omega must remain within the baseband from minus Nyquist frequency to half the sampling frequency to plus the Nyquist frequency. Now this must be implemented in a single block because GNU Radio does not allow feedback between blocks. Each block must process the next data, and the stream must be linear. So if there is a feedback loop, it must be within one block, and this is why you have a ready-made Qpsk loop block in GNU Radio. So we now have all the tools for addressing a real GPS signal. But before we start focusing on the tracking and acquisition phase of GPS, we can actually consider whether the collected data, so if you remember, we're going to use these low-cost digital video broadcast television terrestrial receivers used as general-purpose SDR receivers, and we might question whether we actually get some signal. So we have just discussed that by squaring the signal, we cancel the Bpsk modulation, and if we cancel the modulation, we collapse all the energy that is spread in a 1 MHz bandwidth in a single carrier. Now, we will see by the end of this presentation that GPS signal is below terminal noise, so it cannot be displayed on a spectrum analyzer, and yet if we collapse all the energy in the carrier, then we might raise the signal above terminal noise. So this is an example of squaring a GPS signal, as was discussed by Paul Boven in his Observe Hack Make presentation in 2013, and he discussed that this is how the Weissalar radio sonde was measuring the wind speed. Many of these radio sondes are launched every day, and they are used to measure wind speed along the atmosphere, and yet at the time a GPS receiver was too expensive to be wasted for every balloon launch. So the trick was to measure the Doppler shift of the satellite, and then by looking at the additional frequency shift introduced by the motion of the radio sonde as it was rising in the atmosphere, the users could detect the wind speed. So by squaring the signal, we collapse the frequency spread spectrum signal into the carrier, which rises above noise. How can I demonstrate that these peaks are indeed the GPS signal? Well, if I repeat this measurement over and over again over many hours, you see that the peak here is slowly shifting. If you remember, or we will discuss later, that a GPS satellite rotates around the Earth in 12 hours. So a satellite is visible more or less 6 hours from horizon to horizon. And what you see here are the tracks of this squared signal, where we have multiple GPS signals at a given time, each with a different Doppler shift, and this Doppler shift is evolving as the satellite is flying, rising over the horizon, flying overhead, and then dropping on the other side of the horizon. So these are indeed the path, the velocity, the Doppler shift as a function of time, which is consistent with the shape of the trajectory of the path of a satellite overhead. So squaring the signal allows you to detect the GPS signal, and this will be used to assess whether we have indeed collected information in our records. So once we're convinced that the data set that we have collected indeed includes some GPS signal, now we can address decoding these signals. So GPS is a constellation of a fleet of 31 satellites orbiting the Earth at a distance of 20,000 kilometers from the surface of the Earth. They are fitted with various high stability atomic clocks. At some point it was cesium and rubidium, now it's rubidium hydrogen masers. And the objective of these high stability clocks is to transfer a high stability timing signal for trilateration and positioning of a receiver on the surface of the Earth as a solution of position, velocity, and time when more than 4 satellites are visible from the receiver. Some offset might be introduced on the time of flight that will be the cause of the loss of some of the resolution, and indeed by addressing the GPS processing and the radio frequency layer, we have many more applications than basic positioning in addition to using these high stability clocks. So remember, all satellites are transmitting on the same carrier frequency, so that we need a way of differentiating their contribution. So this is the classical decoding digital communication decoding scheme. Usually when we have a remote communication system, this transmitter will try to share spectrum between multiple users by transposing its signal with a local oscillator on a remote side. So this is the transmitter, and on the receiver side, very far away, the receiver will receive this information and try to recover the information. So this is only an intermediate step, this frequency transposition over the carrier radio frequency. So this is a RF signal, this is an RF signal, if only to share spectrum and to match antenna dimension with the application. But at the end of the day, what we wish is to recover the information. So the objective of demodulation is to compensate for any offset between the transmitter and receiver local oscillators. In the case of GPS, there is an additional challenge in that all information, whether navigation data or the identifier, because all satellites are transmitting on the same carrier frequency, need to be additionally decoded in order to be able to recover the information. So in the case of Bpsk, in the case of this GPS signal, we will have two feedback loop in addition to the usual radio frequency feedback loop where the radio frequency offset is compensated for. We need, in addition, to identify which satellite is transmitting at a given time. So these 2 degrees of freedom need to be solved simultaneously, and the only approach during the acquisition phase, which means a cold start, identification of which satellite is transmitting and at which position in space, so with which frequency offset, will be a brute force approach where we will sweep all possible frequency offsets, solving the frequency offset issue, and sweeping all possible identifiers. So this means that during this acquisition phase, we will need to solve 2 issues. We need to solve what is the frequency offset due to whatever physical cause there is, whether they are the Doppler offset or whether it is an offset of the local oscillator. And on the other hand, we will need to identify which space vehicle is transmitting, so flowing through all the possible pseudo-random sequences. So here the problem will be quantized with the number of space vehicles, and we've seen that there are currently 31 satellites in the GPS fleet. And then the second question we will try to answer is how many Doppler shifts will need to be addressed so that we can find the solution, which satellite is transmitting, which will be detected as a correlation peak. So each one of these correlations, trying to find the pseudo-random sequence in a Doppler shifted signal that was received, means we need to make a correlation, and correlation is 3 Fourier transforms. So we see that this operation will be extremely computationally intensive because of all the correlation that need to be processed. So let us first discuss the part of correlation. So first, how do we identify the pseudo-random sequence? This is achieved by looking at the correlation between the pattern, known pattern, this gold code sequence that was transmitted, and the received signal. So how do we actually do this? Here is an example using GNU Octave. So what we're going to do is, let's say we have received a noisy signal. So we have a signal S, which is a random sequence, let's say 32,000 sequence long, 1 vector wide, and this pseudo-random sequence, this noisy signal might be carrying some satellite signal. So let's say we have satellite number 1, and we say that the random sequence of satellite number 1 is the code of satellite number 1 is a sequence 1024 bit long, but this sequence is random. It will create a unique correlation peak, but it is known. What is important is that it is known. Now, if I plot the autocorrelation of the S1, and correlating requires loading the signal processing toolbox, I can plot the autocorrelation of S1. And what I see here is that the autocorrelation of S1 is a triangular shaped signal. Why is it? Because I have this rectangular window in which I've created a finite duration signal, and I'm running integral of exponential of signal t signal of t plus tau. So what it means is I'm sweeping this signal over it's a reference signal. So here only this tiny part overlaps. Then if I look later, here we have a complete overlap, and if I go a bit further in the future, I will have partial overlap only. So what we see here is that this triangular shape is actually the overlap of the reference signal with the measurement signal, and needs to be cancelled out. How do we cancel? Otherwise, this correlation peak might be here on the side, and if I just search for the maximum, I might be confused by this local maximum. So how do I make sure that I do not have this background shape? I always make sure to remove the mean value of whatever pattern I'm correlating. And if I remove the mean value, now I have a flat background and only a unique correlation peak. So same story for S. We always remove the mean value from whatever quantity we wish to correlate. Now let's say that satellite number S1 has transmitted over signal S at time, say, 1000. So we say that signal from 1000 plus 1, which is the same to 1000 plus 1024, is overlaid with the signal of S1. So we add S1, and now if we plot the correlation not of S and S1, of S1 with itself, but S and S1, we see now that we have a first correlation peak here, which is the presence of S1, signal that was transmitted at time 1000, so that's 1000 from the beginning of the signal, and we can repeat this many times. So let's say that the same signal was transmitted at time 10,000. Well, now we create a second signal, and if we correlate, if we plot the correlation, now we've got the second signal. If we were to watch the raw signal, it would be very challenging to know that the signal was transmitted, because S is a noise and S1 is itself a pseudo-random sequence with the same power. And we see now that we have two sharp peaks, which are only one chip wide, one sample wide. And we see here that the first satellite has transmitted twice. We can repeat this one more time at time, for example, 22,000. And now we will have the second communication, the third communication of satellite number 1. So we have here the third communication from the satellite. Now imagine that a second satellite is transmitting, so we create a new pseudo-random sequence for satellite number 2, which is also 1024 bit long, and now we know that we must make sure to always remove the mean value of whatever we're going to correlate, and this new satellite is transmitting, say, at times 16,000. So at time 16,000, the satellite number 2 has communicated, but we wish to find this communication of satellite number 2. So number 2 is over here. In order to detect satellite number 2, we cross-correlate with satellite number 2. And surely enough, we get the correlation peak at this position. We can repeat, of course, a transmission of satellite number 2 at times 19,000, and we will get a second correlation peak from satellite number 2. But the amazing thing is that because this correlation is linear, we can now also plot the correlation of the same S signal, but this time with satellite number 1. And now we can detect when satellite number 1 has transmitted, when satellite number 2 has transmitted, and we have the timing capability where we can know with one sample wide accuracy when each satellite has transmitted. So this correlation allows us to identify which satellite has transmitted as which time. This is half of the story because GPS is a Bpsk, and in addition to knowing that a satellite has transmitted, we wish to know what was the phase that was transmitted by this satellite. Now, if you look at the expression of correlation, you see that the correlation is the integral of S, the signal, times the pattern time shifted. Now, imagine that we consider the correlation not of the signal and its pattern, but the signal that was time shifted by phi and the pattern m. If we consider this cross correlation, this is equal to the integral of exponential ej phi times the pattern at offset tau dt. That's the correlation with a time offset tau. But because this phase is not time dependent, I can bring it out of the integral, and this is equal to exponential of g phi integral of s of t pattern of t plus tau dt. And what we see here is that this term over here is indeed the cross correlation of S and M as we've seen earlier. So the conclusion is that the correlation of exponential of j phi s and m is equal to exponential j phi cross correlation of s and m. So this means that whatever phase has been introduced during transmission will be recovered at the output of the correlation here. And this will allow us to recover the phase information that was transmitted by the satellite as we are running the local copy of the pattern. So this is what we illustrate on this MATLAB script. What you see here is two copies of a signal. We've created one signal shifted by a phase of 0.8 radian, another one shifted by minus 0.8, and what you see here is after plotting not only the magnitude but also the angle, the phase of a cross correlation, we get one output at plus 0.8, that's the output of this correlation here. We get an output at minus 0.8, that's the correlation over here. And we will see a bit later that this phase is pi dependent, so there is an uncertainty of a factor of pi. We see that we have plus 0.8 and 0.8 minus pi. We have minus 0.8 and minus 0.8 plus pi. So here we see that the phase can be transmitted and recovered after cross correlation as we have just seen. So the cross correlation will allow us to know which satellite has transmitted at which time, and in addition which phase was transmitted. So that concludes the introductory topics, and that allows us to start now challenging the recorded GPS signal. So we have now a complete understanding of the GPS satellite data structure. We have individual chips that are transmitted at a rate of 1.023 mega sample per second, or megahertz. So that's an interval of 1 over 1.023 microsecond between two bits. 1023 of these bits create one pattern, so that the pattern repeats every 1 millisecond, and every 1 millisecond we will get one correlation peak. The phase of this correlation peak will be the XOR between the navigation message and the pattern that was transmitted, so that now that we've cross-correlated with the pattern, we're only left with the phase value of the navigation message that was transmitted. Each navigation bit is transmitted for 20 milliseconds, 50 bits per second, so that we have 20 repeating same phase value of a correlation output. And by looking every 20 milliseconds at the phase value, we can recover the navigation message. Now, to reach this solution, we need on the one hand to identify which satellite is transmitting, solving for the code, and we need to know what is the local oscillator, so what is the frequency offset. And to do this, we've introduced earlier that the number of local oscillator steps that we need to analyze will determine how many Fourier transform will need to be performed, because it will define how many correlations need to be achieved. And so having understanding of how many local oscillator steps will be mandatory. Now, prior to actually testing this hypothesis, we can read data and try to check whether data are indeed valid. So you will have a link to some of the data sets. These data sets that we are sharing has been collected using these DVB-T receivers, and they are binary files, which are the basic storage format of this DVB-T output. These are 8-bit data, unsigned 8-bit integers that need to be read, and we need to know that they have been sampled at 2 megasample per second. This you cannot know, so 2 megasample per second is the data rate. So we open the data file, we read the data from this file, so we need to freed from the file descriptor an infinite number, which means the whole file of unsigned integers. 8-bit, we close the file so that we can reuse it later, and we make sure that we separate the imaginary and real part. So the real part is the even index from which we subtract the mean value, and we create the imaginary part as the odd indices of the data. Sorry, the real part is the odd, and the imaginary part is the even indices, whose value we subtract minus 127. So we might wonder whether there are actually signals in there, and to check this we can autocorrelate, because autocorrelation, even if there is a Doppler shift, if I have a signal with the pattern of the pseudorandom sequence of one gold code, which is time shifted by delta omega t due to the frequency offset, because the correlation will multiply with the complex conjugate of this term here. So it will be s of t exponential of delta omega t complex conjugate. This means that when I do this, these two terms, exponential of delta the omega t and exponential j delta minus omega t, will cancel out, and we see that any leftover Doppler shift will be eliminated in this cross correlation. So I can try to plot the cross correlation. I will not take the whole data set. I can only take the first 100,000 samples. I can plot this cross correlation, and I take the magnitude because d is a complex number. And if I plot this correlation peak here, what I see is actually this correlation peak, which I can make a bit nicer by plotting it by itself instead of a light yellow. So here is the autocorrelation of the signal, and if I look closely close to the carrier here at from 100,000, I see these side lobes, side correlation lobes. I see here that the center is at 100,000 because I'm sweeping 100,000 long samples, so that I have a 200,000 output data set, and I see now that this side lobe is at this is visible on the bottom left corner here, is located at 98,000. This is located at 102,000. So we have cross correlation side lobes at minus 2,000 plus 2,000, which at a sampling rate of 2 megasample per second indeed means that we have side lobes at minus 1 millisecond and plus 1 millisecond, and then we've got the next ones over here, that's 94, so we have all these additional side lobes. So the fact that we have these side lobes on the autocorrelation function is the proof that indeed there is a GPS signal to be analyzed in these data sets. So we are convinced that there is some information to be analyzed. So now we need to assess what is the range of a Doppler shift that needs to be swept. Now the Doppler shift will be found as a solution of the orbital parameters of the GPS satellite. First of all, we need to know the linear speed at which the satellite is flying, since the linear speed, this vector v here, will determine the projection to the users. So the linear speed v is of course given as the distance along the orbit, so that's the circumference of the orbit, so the distance divided by the period, so the time it takes for the satellite to rotate around the Earth. So the distance, that is the radius of the Earth, plus the altitude h of the satellite, and the radius of the Earth is, at some point, the definition of the meter was a fraction of the circumference of the equator, so that would be 40,000 kilometers divided by 2 pi, which is about 6,400 kilometers for the radius of the Earth. And the altitude of the satellite is 20,000 kilometers. So that's easy enough. We have the total path that is traveled by the satellite. The period of a satellite can be found by using Kepler's law. We know that t squared divided by the radius cube is a constant, which is the gravitational constant. And if we know that a geostationary satellite, which by definition is a satellite that always stays at the same position in the sky, so it has a period of 24 hours, is at an altitude h of 36,000 kilometers, so that's the altitude of geostationary satellites, then it means that if I consider the case of geostationary satellites which are located at the center of the Earth plus the altitude of a satellite 36,000, this is taken as a cube. On the top I take the radius of the Earth plus 20,000 kilometers, the altitude of the GPS satellite, and I take the square root of this guy. That tells me what is the period of GPS with respect to the 24 hours of the geostationary satellite. So if you do the calculation here, you will find that the period of GPS is 1/2, 0.5, the period of the geostationary satellite, which is 24 hours. So every 12 hours, a satellite will fly the circumference of its orbit, and this will give us the linear velocity, which is about 4,000 meters per second. Now we can address what is the projection angle. So if we say that when the satellite rises above the horizon, the user is located at a distance r, the radius of the Earth from the center of the Earth, and the satellite is located as a distance r plus the altitude h. So we have this angle here, which is related to the cosine of this r over here and the r plus altitude over here. And this angle over here is the same as the angle over here, so that we are left with the fact that the projection of the velocity is equal to the linear value of the velocity times the radius of the Earth divided by radius of the Earth plus the altitude. If you do the calculation, you will find that the Doppler shift, so the Doppler shift is equal to the Doppler shift delta FD is equal to the carrier frequency, in our case 1.57 gigahertz, multiplied by the velocity projected divided by the speed of light. And if you do this calculation on the Doppler shift, carrier frequency, velocity of the projected velocity divided by speed of light, you will find a Doppler shift of plus or minus 5,000 hertz, plus or minus 5 kilohertz. So what we would like to address is how to distribute this plus or minus 5 kilohertz. What is the frequency step within the plus or minus 5 kilohertz? If we want to convince ourselves of the validity of the calculation, we can check experimentally what are the actual Doppler shift of measured carrier frequencies. This is the output of the GNSS SDR software-defined radio decoder, and indeed you see that we're more or less from plus or minus 4,000 plus or minus 4,000 hertz, which matches the calculation we just did on the Doppler shift. It's a bit less because this antenna cannot go all the way to the horizon, so it's slightly less. So we have plus or minus 4 kilohertz, and now the question is, what is the steps that we need to address? Now, the second issue is we have started with the frequency due to the Doppler shift, but there is also the local oscillator offset. And now we're using these low-cost DVB-T receivers, and these low-cost DVB-T receivers do exhibit some poor quality oscillator. In this case, we're measuring the output of 100 megahertz hydrogen maser, and we see that the frequency is offset by 7.2 kilohertz. So what is the uncertainty on our inaccuracy of the local oscillator? You see that it's 7,200 hertz divided by the 100 megahertz carrier. If I take ppm, I remove the megahertz, and I'm left with 72 ppm. 72 ppm at 1.57 gigahertz, that will be a 113 kilohertz offset. So you see that on the one hand we have plus or minus 5 kilohertz offset due to the Doppler shift, and we might have up to 120 kilohertz frequency offset due to the poor quality local oscillator. So this is one reason why we need high quality local oscillators in GPS receiver for fast acquisition time. So we need to address both the frequency offset due to the local oscillator as well as the Doppler shift. So what are the actual frequency steps that we can accept? So let's use the MATLAB Central CA code. So CA code is a piece of MATLAB software for generating the pseudorandom sequences of GPS signal, and CA code will take the space vehicle number and the sampling frequency, so the number of sample per chip. So I can create C1, the CA code, say, of satellite number 5 with 1 sample per bit, and I can randomly take C2, which is the sequence of CA code, number 15 of space vehicle number 15. Be careful that the mean value is not 0, so as usual we must always remember to subtract the mean value of each one of these guys. So we remove the mean value of C1 and C2. If I plot the autocorrelation of C1, I get a correlation peak. Of course, I get the same correlation peak for C2. And if I cross-correlate C1 and C2, I get no correlation peak. So it's all working very well. These sequences match the expectation of an orthogonal frequency. Now, let's say I wish to create a frequency offset, and I'm sampling at 2 megasamples. So that means that the time is, if I create a variable which is the sampling rate, then the time is the sequence from 0 to the length of C1, so 1023 samples, divided by fs. So this is my discrete time, and I can create a frequency shifted code which is equal to the C1 times the exponential of j times 2 pi times the frequency offset, say for example 300 hertz, times t, of course the time. So this is my new of course, if I start time at 0, I need to subtract the last value. So here I create a frequency shifted copy of the pseudorandom code, which is shifted by 300 hertz. And now, if I plot, now that it's a complex number, I need to take the absolute value, the magnitude. If I take the local oscillator shifted with its C1, I get this new correlation, which we see is hardly affected by the 300 hertz Doppler shift. If on the other hand now I am to shift by 1300 hertz and I again plot, well, we see that at 1300 hertz the correlation peak is significantly degraded. If I go even further at let's say 2000 hertz, now I have no correlation peak at all. The Doppler shift is so strong that I can no longer detect the correlation peak. So I need to find the trade-off between the loss of correlation peak due to the Doppler shift and the number of computation I'm going to do. So here is the light blue that I just created with 1600. So the bigger the frequency offset, the worse the correlation peak because of the additional phase rotation. Now, what we might consider is actually that the sentences are 1 millisecond long, so that if we have a 1 kilohertz frequency offset, that would be half a period during the correlation that would degrade the correlation peak. So what we will do is we will consider frequency steps in the Doppler range of 500 hertz, which is a safe bet with respect to the 1 kilohertz inverse of a 1 millisecond duration of the correlation sequences. So based on this conclusion, 500 hertz steps, if we go back to the previous slide, we see that prior to this analysis, we had plus or minus 5 kilohertz. So that would be 20 steps, plus or minus 10, that's 20 steps. And because of the local oscillator offset, we now have a much greater, we have up to 240 times 2, that's 480 Doppler shift analysis that need to be performed instead of the 20 that were initially expected. So you see that the local oscillator offset will have a dramatic impact on our ability to quickly have a convergence. So now let us conclude this analysis. We have this data set that we collected, this data set D, and now we wish to run a correlation. So let us create an analysis script for this sequence. So we have loaded the data D, and what we need to do is to shift for all Doppler shifts from minus 120 kilohertz up to 120 kilohertz, which is what we've seen to be the safe boundary for the local oscillator offsets, with steps 500 hertz. And what we need now is to create the frequency offset. So we take, say, only the samples from D from 1 to the first 100,000 data. And so we create time. Time is the sequence from 0 to length of D minus 1. And this is divided by Fs, the sampling frequency, of 2 megahertz. So this gives us our discrete time, and for each frequency offset we're going to calculate the signal frequency shifted. So that's our D data multiplied by exponential of G 2 pi times T times the frequency offset df. I know that this has to be a vector instead of being a line. And once I have a time-shifted copy, I keep the maximum of index m, where m is a variable that will be incremented at each new step, is equal to the max of the absolute value of the cross-correlation of the data that we just shifted with the pattern that we wish to analyze, so the space vehicle pattern. The pattern will be CA code. I know that in this data set, space vehicle number 18 exists, and this will be at a data rate of sampling frequency divided by 123 E6, because I know that it's transmitting at 1023 megabit per second. So the pattern, we must make sure to subtract the mean value from the pattern. And once we've done this, we have the whole acquisition sequence of a GPS data. So we can run this analysis after making sure that we correct the mistake about the multiplication. So if we run the analysis here, we will see that the calculation will take a bit of time. And what we expect to achieve is a plot of the maximum of the cross-correlation peak as a function of Doppler shift for one given satellite, here satellite number 18. So space vehicle number 18. So the analysis is being computed, and once it will be finished, we will plot the analysis as the maximum, the result of the calculation here, maximum as a function of frequency Doppler shift. So that will be from minus 120,000 to 120,000 with steps 500. So if we plot the maximum, after we hold off to remove the previous chart, and if we plot the maximum, we have here the correlation peak. So you see that it's right here on the right, because we go from minus 120,000 to plus 120,000, meaning that there's a whole range of local oscillator frequencies that do not make sense. If we actually narrow down from 80 kilohertz to 120 kilohertz, now we will see that the calculation will be, of course, much faster, and once the calculation is completed, we can plot the result of the maximum for this narrower range. And of course, now right in the center we have this correlation peak, which tells us what was the frequency offset when this satellite was flying. To conclude this presentation, if we were to repeat this operation for all possible space vehicle and color encoding the correlation peak, we see here that we have space vehicle number 15, number 18, and 26, which are visible, which is consistent with the output of GNSS SDR. And here are two DVB-T receivers. These are E4000 based DVB-T receivers with plus 59 ppm bias, so that's plus 91 kilohertz, and indeed you see the three satellites at plus 91. Here you see another R820T DVB-T receiver with minus 68 ppm bias, and indeed the data are located around minus 110 kilohertz. So you see that this 100 plus or minus 150 kilohertz range significantly increases the time it takes to do the data acquisition, and in this case, for example, it takes about 300 seconds on a MATLAB computer, general purpose computer, to compute these correlations. So these are the charts that compare our output with U-Block's U-center output, and again you see here this correlation peak separated once every millisecond. This is the repetition of the correlations from the satellite messages that would allow us to recover the navigation data. These are consistent with the U-center output, and if you were to finish the acquisition step, then you can go for tracking, because you know that the satellite is not going to suddenly vanish from the sky. So once you know which satellite is located at which Doppler shift, you replace the brute force approach with a phase-locked loop. The phase-locked loop will track the phase that was identified after the coarse analysis of the Doppler shift, and if this time we replace the arctangent function of Q over I with arctangent of Q arctangent 2 of Q and I, which remembers the sign of individual Q and I. If you take arctangent of Q over I, you see that positive divided by positive is equal to negative divided by negative, or the opposite here. But if you take arctangent 2 of Q and I, then you don't have this pi uncertainty, and you can recover the Bpsk. These are the Bpsk navigation messages. So this concludes the analysis of the GPS data. If we now conclude this whole discussion by analyzing the link budget using the Freeze equation and the fact that energy spreads over a sphere of 4 pi d squared, then we have free space propagation loss estimate, which states that we have when we go back into decibels, so the square of the decibel, we make it 20 log of the wavelength, and the wavelength is frequency divided by velocity. So we have here 20 log of the frequency. This does not mean that the system is dispersive. It simply means that the area of the antenna on the receiving side is smaller as the frequency rises, plus log 10 of the distance over here, and minus the c over 4 pi, that's the constant for converting lambda, the wavelength, into a frequency, and 20 log 10 of c over 4 pi is minus 147. So if we do the calculation that a satellite located at 20,000 kilometers from the surface of the Earth, emitting around 50 watts, will have a free space propagation loss of 182 dB, the numeric application of the previous Freeze equation, will with a 157,542 gigahertz frequency, then it means that the initial 47 dBm dropped to minus 122 dBm on the surface of the Earth, which is above the standard of the US Air Force that states that the GPS signal must be more than minus 130 dBm at the surface of the Earth. Comparing this with the thermal noise, the bandwidth of the signal is 1 megahertz, or that's 60 dB above the thermal noise floor at room temperature of minus 174 dBm per hertz, and that means that the thermal noise is minus 114 dBm, which is above minus 122 dBm. But thanks to pulse compression, by collapsing all the energy that is spread over the 1 megahertz bandwidth into the carrier, we see that the 1023 bit, so the 1000 bit long sequence will improve the signal to noise ratio 1000-fold. 1000-fold is 30 dB signal to noise ratio gain, and we see that the minus 122 dBm raised to minus 92 dBm, which is above the minus 114 dBm. So thanks to the energy collapse into the carrier, when correlating or when squaring, we see that the signal rises over the thermal noise. So from this presentation, we conclude how we have addressed the benefit of correlating for improving the signal to noise ratio, for accurate time of flight analysis using correlation. The width of the correlation peak is equal to inverse of the bandwidth. We've seen how to detect CDMA signals, how to identify which satellite is transmitting by correlating with the CA code. By sweeping the Doppler shift, we can identify the frequency offset of a signal, and finally we mapped the acquisition phase where we were able to identify which satellite is transmitting at which frequency. Thank you for your attention.